Okay. 150-ish, 180 years ago, something like that, Dr. Lewis got frustrated. And scientists at the time, mostly chemists, sometimes physicists, would be able to create a formula, but they didn't know what the molecule looked like. So Lewis went to work and came up with this process by which you can have trial structures based on the formula. Okay, so it's based on valence electrons, and we haven't talked about valence electrons yet. Um, so now there are two kinds of electrons in the outside the nucleus, and there's electrons inside the nucleus as well. I'm talking about the ones outside the nucleus. There's two kinds. If we look at something like um, carbon, now carbon's got 6 electrons. Now, if you remember, Bohr came up with the planetary model for electrons. And so we have a nucleus here. And what Bohr said, and Lewis is using Bohr's model here. Okay, so we have orbitals, and the inner orbitals are very small compared to the outer orbitals. So you can only fit 2 electrons on the inner orbital. The next orbital, and later on they come up with, it's not just one orbital, it's multiple orbitals tied together. But the next set can hold 8 electrons, but we only have 4 electrons left. We put 2 in the inner orbital, 4 in the outer one. Now, carbon is a special case. And when you take 1A or possibly 2A, you're going to talk about why carbon is a special case. It's called bond hybridization. That's out of the scope of this class. So just know that it's got 4 electrons. Okay, so the outermost electrons are the valence electrons. And those electrons, except for the noble gas electrons, are unstable. And as you know, in the universe, things go from want to become more stable. So that's the driving force for atoms wanting to combine with other atoms, is to become more stable. And then underneath the covers, it's those unstable electrons that want to become more stable. So those are the electrons where all the chemistry happens, are the valence electrons, except for noble gas valence electrons. And the reason why those don't come into play is they're already extremely stable. And later on in Unit 3, we're going to talk about why the noble gases are more stable than the other elements. Why are those valence electrons more stable? Okay, the other electrons that aren't valence are called core electrons. Core electrons are below So the valence electrons are in an orbital outermost. Doesn't matter how many orbits the atom has. Like uranium's got 92 electrons. So there's a whole bunch of orbits, but only the ones in the outermost are valence electrons. All the others are core electrons. And core electrons are extremely stable. So they don't come into the play because they're already stable. Only the valence unstable ones are the ones that come into play. So those are the valence ones is what Lewis worked with. And every atom has different numbers of valence electrons. Now, the ones circled are the ones that you need to memorize. There are only, what, 5 of them. And basically, they go across period 2 up there in the periodic table and hydrogen. And all it represents are the valence electrons for those 5 elements. Now, because in the periodic table, everything vertically, remember, in a group has very, very similar chemical characteristics. The reason for that is they have the same number of valence electrons. So if you look under carbon over there, see, underneath carbon is silicone. Silicone has exactly the same number of valence electrons as carbon. Hence, its chemistry is the same. Sodium. Sodium has 1 valence electron. Potassium underneath it has 1 valence electron as well. Hence, the chemistry is the same. That's really important to remember. It boils down to you have chemistry of the top element, which is the same as the chemistry below. Now, the transition metals in the middle are, some of them are kind of wildly different. Yeah. Yes. The one period going across, is that what you mean? Oh, yeah. 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 And columns are called groups also. Okay. So valence is the name of the game as far as chemistry goes, except for nuclear chemistry. We're talking about non-nuclear chemistry here. Okay. So what I've put together are a set of rules here and steps. This is located on in Unit 2 files. Now, there are 2 ways to do Lewis dot structures. I've simplified it greatly. That's what these are. There's another way to do it, and it's more involved. I think this is much easier, and students can do this much easier. Okay, so step 1, excluding hydrogen or halogens. Start by putting the atom with the most singleton electrons in the center and arrange the other atoms around it. Okay, so let's use water as an example. Let's start from scratch here. So, as you know, H2O so notice water now. Water's got oxygen in it, and oxygen has 6 valence electrons. Notice that we have 2 pairs and 2 singletons. When I say singleton, that's a single electron. So we've got, this lower. So these are the pairs. These are the singletons. Nitrogen. It's got 1 pair because it has 5 valence electrons and 3 singletons. Now, the singletons is where bonding occurs. Bonding is when an atom combines with another atom to become more stable. They do that by combining electrons. The electrons being combined are the singletons only, not the paired up electrons. So for every singleton, that can be a bond. So how many bonds do you think oxygen can have? Ask yourself, how many singletons are there? Two, so two bonds. Nitrogen, how many bonds? Three singletons. Okay, so it's 1-to-1 correspondence between singletons and bonds, because when one singleton comes in contact with another singleton, they share the electrons. And that's where the stability is derived, from that sharing of those two singleton electrons. Now notice sulfur over here. Look at sulfur, look at oxygen. Notice sulfur is exactly the same as oxygen because sulfur is underneath oxygen on the periodic table. Okay, so we need to know about oxygen. Oxygen has two singletons, two pairs. Hydrogen has one singleton, hence one bond. Okay, so now let's look at water again. Oops. Now we have hydrogen, one singleton, oxygen's two singletons and two pairs. Now, when you draw these, doesn't matter where you put them, as long as the pairs stay together. No exceptions, because the pairs are already two singletons put together internally. So it can't bond anymore. That's why it's important to keep those together. You can also move them around for convenience sake. So step number 1 says, put the atom with the most singletons in the middle. That's going to be kind of your base, because it gives the most combinations. Hydrogen has one singleton, so it's the least complex. Same with halogens. They only have one singleton. They have 3 pairs and one singleton. Okay, that's step number 1. Step number 2 is connect the singletons up. So the singleton on oxygen, singleton on hydrogen. Now, there's another singleton on oxygen, but it's not very convenient. So what I'm going to do is I'm going to move stuff around so it's more convenient. As long as you keep the pairs together, singletons by themselves. So I'm going to move this pair here up here. So we still have 2 singletons, 2 pairs. Okay, so that's step 2. Connect everything up with one bond. And again, singleton to singleton shares, forms a bond. Now, how many bonds can oxygen have? 2, because it's 2 singletons. How many bonds does oxygen have up here? 2. So it's a legal structure. And there's some rules on what's legal and what's not legal. Okay, the next step is evaluate each atom has a full shell. Now, when I say full shell in this class, I'm talking about 8 electrons, except for hydrogen, has 2 electrons. And in Unit 3, we're going to talk about what a shell is, what a subshell is, what an orbital is, etc. But right now, think in your mind, octet. 8 electrons. Okay, so let's count them. Okay, oxygen, now this includes the shared singletons. So we've got 2, 4, 6, 8. So oxygen has 8 electrons, full shell. Hydrogen, remember, its full shell is 2 electrons. How many does hydrogen have? 2 electrons, each one. And there are no lone singletons out there, unbonded. That's called a free radical. Very, very, very unstable. That's what happens when you go out in the sun and you oxidize omega-6 fatty acids on your skin. What happens is that fatty acid oxidizes and forms free radicals, which can lead to cancer. So free radicals are bad, bad items. Okay, so the next step is evaluate this molecule. Okay, it's got a full, oxygen's got a full shell, hydrogen's got a full shell. You need to make sure that the bonds are correct. Hydrogen has 1 bond, 1 bond. Oxygen has 2 bonds, we have 2 bonds. So this is considered a legal Lewis structure for those 2 items. Full shell and the bonds are legal, the numbers of bonds. So this is a list of all the atoms, how many bonds it should be making. And that also corresponds to the number of singletons. Because 1 singleton can form a bond with another singleton. Okay, once you know it's legal, then you substitute the bonds with a straight line. Yeah. The shared ones, yeah. Because you have to focus on each atom, not the whole molecule. Each atom has to fulfill those 2 steps, octet and number of bonds. So you go through all the atoms and make sure they're all legal. And if all of them are legal, the whole thing is legal then. So if one of them has like three bonds that should only have 2, well, then you have to redo stuff. Yeah, but yes, it's got 6 electrons. So the way they're organized, though, is in 4 of them are in pairs, though, and the other 2 are by themselves, the singletons. So the singletons are the ones that are going to do the sharing with another atom. Sure. Okay, then the next thing we're going to do is replace the bonds with solid lines. So we're going to redraw this. And there's a bond here, solid line, and we keep the pairs as part of the Lewis structure. So that's the Lewis structure for water. I've got a lot of worksheets for practice on this and files, unit 2, quite a few. Now for the lab next week, we're going to be only doing the neutral atoms, not the ions. If you want to do the ions on your own, that's fine. And I can check them off for you. But the ones I'm looking at when I look at your lab are going to be the neutral ones only. Okay. So everyone okay with water? I'm going to do a lot more examples here. Okay, so let's do Oops. Okay, so let's do carbon dioxide. Now, carbon's got 4 valence electrons, 4 singletons. Oxygen has got 2 singletons. So which is going to go in the middle, carbon or oxygen? Carbon because it has more singletons. Okay. I'm going to put carbon in the middle. And then oxygens, we're going to surround that carbon. And I'm going to put the pairs together. Just going to move around like I did with the water. Okay, so that's step 1. Step 2 is to make a single bond to each atom, connecting up singletons now. And once you do the one bond, you ask yourself, are there any singletons unbonded? Yes. They have to all be bonded. So, next step is to just continue bonding. Now notice over here on the left, we have a situation. Is that I can connect the 2 singletons, but it's going to cross over. So I'm going to redo this one here. And bond with this one instead. That way I won't have to cross over. Okay? Now, again, are there any singletons unbonded? No, they're all attached. So now we're going to move on. We need to evaluate this. Is this a legal structure, the way it's written? Okay. Do all 3 of those atoms have octets, including the shared ones? Let's look at oxygen on the left. 2, 4, 6, 8. Oxygen on the right, 2, 4, 6, 8. Now, how I got 2, 4, 6, 8? The pairs count, the singletons bonded count. So we've got 2, 4, 6, 8. Carbon in the middle, 2, 4, 6, 8. So this is a legal structure so far. Carbon needs 4 bonds. How many does carbon have? It's bonded 4 times. That's good. Oxygen bonds twice. For each one of these, bonds twice. Now I want you to notice something that's different than the water. The carbon-oxygen bond has 2 bonds going to it, where this is 1 bond. Same over here. So this is called a double bond. Now you can have, carbon's got a combination of 4 bonds. That's a combination of bonds. So carbon can have a triple bond and a single bond, because that adds up to 4. 2 doubles, Spock would be proud, 2 doubles, 2 plus 2 is 4, or 4 singles. As long as it adds up to 4, it's fine. Oxygen's 2. So it can be 2 singles or a double. So this is legal. So now we're going to replace the lines. Oops. So that's the electron dot structure or Lewis dot structure for carbon dioxide. Okay, how are you guys doing? Is this making sense? Okay, so let's try another one. Now remember the golden rule in this here. Each atom has to have its number of bonds and an octet. Sometimes, however, you can have more than one legal structure. For example, so we've got C2H6O. Now this is going to have more than one legal structure, both valid. In fact, one of the legal structure is drinking alcohol, ethanol. And the other one is dimethyl ether. So, same rules though. And if you do a search online for a tutorial for doing Lewis dot structures, don't, because they're not going to use the same rules that I'm using. They're going to be more common in terms of complexity. The rules, when you do the search online, are universal rules. They'll apply to everything in the world. Mine apply to a fairly large number. It's just that not as extensive. So textbooks don't use my rules. Ferguson's class uses my rules. You end up with the same structure. It's just the concepts are easier to understand the way I do it. The way the book does it is you have to count all the valence electrons and you have to move everything around. It's much more complicated. So, okay, so what do we put in the middle? Which of those three atoms have the most singletons? Carbon. So the carbons go in the middle. Then we have the lone oxygen, which is next. Let's stick it over here on the right. It really doesn't matter. Then we have 6 hydrogens. Okay, so that's step 1. Now, step 1 says put the one with the most singletons in the middle. However, you can deviate from that a little bit. So I'm going to redo this with the oxygen in the middle and the carbons on the outside in a minute here. Let's do this one first. Okay, next step is connect everything up with one bond to start with. Okay. Do we have any lone singletons running around? No. So everything is connected up. Okay, now let's check for whether it's legal or not. Okay, let's check for octets for the carbon and the oxygen. So the left carbon's got 2, 4, 6, 8. The right carbon's got 2, 4, 6, 8. And I'm counting bonds now. And if there's an electron pair, oxygen on the right, it's got 2 bonds. So that's 2 plus 2 is 4, 6, 8. Okay, and the hydrogen's got 2 all the way around. So full shell wise, it's fine. What about number of bonds? Carbon takes 4 bonds because it's 4 singletons. 1, 2, 3, 4. 1, 2, 3, 4. Oxygen's 2 bonds, 2 singletons, 1, 2. So this is a legal structure. Next step is we put lines in for each of the bonds. So that's what it's going to look like. And that's drinking alcohol, ethanol. Okay, is everyone okay with that? Okay, so let's try another structure using the same formula. Yeah. The pairs. Okay, a bond is a pair of electrons. They're already paired. That's why they don't connect. Now, there's an exception, a very, very small exception to that. That's out of the scope of this class. But as far as we're concerned, pairs are already paired up. That's why we don't count them. Good question. Okay, so let's, instead of putting the carbons in the middle, let's put the oxygen in the middle and surround it with carbons. Putting the carbons in the middle is always a good starting place. And then check to see, and the more complicated the formula, the more options you're going to have. Okay. Now we have the oxygen in the middle. Connect everything with one bond to start with. Okay, no singletons left unbonded. So the next thing we're going to do is see if it's legal. Okay, left carbon, 2468. Right carbon, 2468. Oxygen in the middle, 2468. So they all have octets. The hydrogens have a full shell of 2 electrons as well. So now we connect up. So it's a legal structure. 4 carbons for carbon, 2 carbon are 2 bonds for the oxygens. Legal structure. Okay. Now we just do the lines. So both those structures, this alcohol and this ether, are legal Lewis structures for that formula. So again, the more complex the formula, the odds are high that there's going to be more than one legal structure that works. Yeah. Which one is it? Okay. That's the dilemma chemists face. So then the next step for a chemist would be to take that compound that generated that formula and do some testing on it. Is this an alcohol or is it an ether? And you do standard alcohol tests, standard ether tests, or you run it through a machine like a spectrophotometer or uh, a chromatograph or something like that that would tell you more of the structure. But right, that's the dilemma. Okay, both these are legal. Which one is it? And then you have to do further testing. Otherwise, no way to tell. Exactly. All right, does this make sense? This just takes practice. So I'm going to give you a problem that has uh, okay. There are at least 5 legal structures for this. For those of you in Friday Lab, if you'd like to come up and get your tests. And I have a friend named Destiny. I've known her since she was in junior high. My daughter's a good friend. What's her name? Megan? I hate doing that test. And Holly normally sits there, right? Here, spread those out. The initials are, and you can grab one for your buddy as well, not a problem. For sure, that's probably gonna be the last one. Yeah, one's a take-home test. Back, why don't you staple it? You said you're Megan, right? Oh, I think that's the key. They always do really well. That person called named Keith. Every time they always get 100%.
Minus A. Would you get? And you go to B?
Yeah,
Hey.
everything else I got them.
Wait up.
Oh, I got it.
Where the heck is my initial?
But it was supposed to.
Did I get the right? I think it's 7 times 10 to the 14th. Yeah, you're fine.
You got 10 to the 14th though, right?
I got 10 and 13.
13.
Are all the tests called on the third one?
Theoretically. Now,
Could look at it later, but I want to know how to do it right if I got
okay, we can go over that.
Yeah.
Now there's another Megan as well.
it. Not me.
That's you?
Yeah.
Okay.
This is-
Mhm.
Oh, thank you. Oh, can I find
What's your name?
a two cent? A.
How about everyone? Uh, it says I got a -20 for no take home test. Is that the take home problem? Yeah, and I got the right answer.
And you got the right answer.
Yeah. So shouldn't I only have 2 points off? So
20. This is gonna be jacked up a lot. Are you in Friday or Saturday?
yeah, so I should have like.
I don't know how I missed that.
It's all right. I mean, I'm glad I got it.
Better, huh? Okay. Send me an email or follow me to lab. Because it's not updated. Oops, it's not updated.
I'll send you the attendance message. Does that work?
Yeah, that's fine. That's a good one to do. These making sense? Yeah. Good. Other people don't get the cyclic one. Yeah.
Those are all right. Punch this one. That's not a lot.
Is this a double bond? Yeah. Um,
Sorry.
yeah, that's fine. I think there were five. I'm trying to remember. I think back to, I used the same example last semester. I'm trying to think over the summer. Seemed like there were five. Well, there's another one you can do a double bond in the middle.
Double carbon bond?
Yeah.
Oh.
And then have, also,
Can't have any double hydrogen bond.
you don't have, this is acetic acid and you don't have acetic acid. That's another one. Which is a double bonded O and a single bonded O under the same carbon.
Carbon.
And that's the same one you had up here. This is the one I'm thinking about. And there's two versions of this too.
It's not the same. I have the double carbon bond.
This one here is dead. You got COH, 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 COH. Same one. So that's acetic acid. And then what you can do is do another one, put the OH over here, H over there.
Okay.
Yes. Oh, yes. there
And then, is there a way to look at the periodic table and know how many bonds and single ribbons are on? Or you just have to memorize it?
No, the only problem is carbon. So if you remember, carbon is 4. And then either side of it, if you go to the right, it increases by 1. If you go to the left, it decreases by 1.
That's the number of singletons that increases and increases.
Actually, it's the number of valence electrons increases you go to the right, but you can't go over. This is the problem. When you go to 1 over, it's nitrogen. Nitrogen has 5 valence electrons. So you have 1 pair, 3 singletons. So you go 4 valence, 5 valence for nitrogen, but you start pairing up stuff. Starting at nitrogen, you're pairing up stuff.
I had 1 pair and I had 2.
Then yeah, the oxygen, it gains another electron. So that pairs up 2 more. And then when you go to fluorine, yeah, and a singleton, you have 7 there. And then when you get to little neon, noble gas, and you've got 8 electrons, 2, 2, 2, 2.
Okay, so, okay.
So the noble gas has got all pairs. That's why it can't bond. And very stable, yeah.
And
So within itself, it's got an octet. It doesn't need anything else to achieve an octet. Where the other ones have to bond with something to get an octet. That makes sense?
yeah, I'm trying to piece the rest of the table together, but
And those are the only ones you really need to worry about. And then everything in the group. So if you know oxygen, you know sulfur. You know nitrogen, you know phosphorus. You know, they're the ones directly underneath.
does that continue all the way down? Or
Yeah.
just okay.
It's very true the closer you get to the top. Things get a little, when you get really these complicated atoms, all kinds of stuff happens. But in general, yes. But see, the problem is you can have more than an octet when you get to period 3. So that complicates things.
Let's stop.
Yeah, that's how the scope of this class.
Didn't know what to turn it into last night. So I turned it into the test retake portion of it. I didn't know.
And what do you mean?
There was a thing labeled test retakes, where
That was for tests, yes. Just
should I like
just email it to me.
I'll try. The CAM scanner app that I'm using, it doesn't give me an option to email it. It only gives me an option to turn it into an assignment.
Right, just do the 1 page, save it out as a PDF and email that to me. And in the email, mention that you turned it in yesterday. Because that way, remember I said it's due by midnight? And you did fulfill that. I just want to give you credit for it.
Check my phone from Tom.
Yeah. Mark. You Mark? No. There's 6 of them. The one that she came up with is another one that's different. than that. Yeah, there's 6 of these variations. Yes, that's fine.
Options 4 bonds. Where's that coming from?
Not 4 bonds. Carbon needs 4 bonds. 1, 2, 3, 4. Oxygen needs 2 bonds. It has 2 singletons.
And then hydrogen only has 1 singleton, so.
1 bond.
Okay, and then when you say it's a legal structure, you keep saying it's a legal structure, it has, and I can't understand.
2 reasons. Okay. 1 is octet. So 2, 4, 6.
What's that?
That's 8 electrons, including the
What word are you saying? I can't understand.
octet. Like as
Oct-
tet, T-E-T. Octet.
And then what does that mean?
Octa is 8. And that's a group of 8.
Has a what though?
Electrons. 2, 4, 6, 8. 2, 4, 6, 8. So when you're counting the electrons, you have to count the pairs and the bonding pairs, or the 8.
But I mean, there's not 8 in this whole structure.
Mhm.
So,
2, 4, 6, 8.
well, does this,
No, you're doing it per atom. Per atom. So cover everything except the atom.
but then I guess as we go through it, I get confused because then this is part of this, so we go here. You know
Yep.
what I mean?
Right, and then we do this one.
Okay.
Cover those up.
Okay.
2, 4, 6, 8. 2, 4, 6, 8. 2, 2, 2.
Okay.
And then, okay, that's octet, and then number of bonds. So carbon needs 4 bonds, right? 1, 2, 3, 4. 1, 2, 3, 4. Oxygen needs 2. 2. Hydrogen's 1 apiece. So yeah. So there's 2 steps in that legalization process.
Well, and if it has 4 bonds, I don't really need to count the 8. That means it has 8 as well. So,
You can multiply 2 times 4 in your head. That better?
yes.
Yeah, and that's fine. Yeah, could you show that to him? This was another one I forgot about. Yeah. This is called a peroxide. When you have 2 oxygens together like that. You see, he's got all these.
Yeah.
So this makes sense. How are you doing?
What it has to be like this. To help you to
So if it has 2 below it, it's 2 of them. So this is going to have 2 carbons, 2 oxygens, 4 hydrogens.
There's too many extras off.
Well, there's 6 you can do. They're legal. You can do it 2 ways. You can do it in Outlook or you can do it in Canvas. You go to Canvas.
account. I can't send it to you in Canvas. I have to send it from Canvas.
You can do it from Canvas. If you go to Inbox, okay, if you want to do it from Outlook,
Well, I guess I don't have an account open on Outlook yet. Should I use my school email?
you're what?
My school email?
It doesn't matter. Did someone fall or? Oh, well, that sucker's loud. Okay, so my email account is T Ferguson 8 at Los Rios. I'm not Los Rios. SierraCollege.edu.
So what?
8, number 8.
Is that how you spell it?
Yeah.
Okay.
Huh?
Can you bond carbon twice?
Up to 4 times. Yeah.
Oh, like each other,
Yeah.
so I can do this one,
Yep.
so does that look correct? Does?
You brought it?
Yes.
So how do you know it's correct or legal?
2, 4, 6, 8.
And 2, 4, 6, 8,
Yeah.
and then oxygen's 2, 4, 6, 8. So yeah,
So everything has to be bonded with 8.
except hydrogen. And hydrogen's got 2. And that's called a full shell,
Shell. So,
like a seashell.
okay, and so this is a full shell, and then this should be, okay. So you and I.
Yeah, and it's by,
Thing.
it's by atom.
Okay.
See, carbon's got a full shell, it's just got 8. This carbon's got 8. Oxygen has got 8 as well. This oxygen's got 8. These got 2 apiece. So everything's got a full shell. That's number one. Number two is how many bonds we have. So carbon needs 4 bonds. 1, 2, 3, 4. 1, 2, 3, 4. Oxygen needs 2 because again, this goes to the singletons. So oxygen has 2 singletons, 2 bonds. 1, 2, 1, 2. And hydrogen has 1 singleton, so 1 bond. So ta-da, it's legal.
Okay.
Now you're gonna redraw instead of these blobs. Exactly. Good.
Oh,
It's different than, it's different than hers.
Yeah.
Yeah, that's fine. You can also do this with the OH on the same side as the double bond over here. That'll be another structure.
Like this OH can be moved over here.
Yeah, swap it with the hydrogen over there on the left side. Take the OH on the right and swap it with the hydrogen. Finish that out with lines and then I'll show you what I'm talking about.
I'm trying to figure out.
Okay, so so you have a problem though, is oxygen only has 1 bond, it needs 2 bonds. There's 2 singletons.
you keep the 3.
Oh, yeah, that's very important.
The file he's referencing of like that tells you how many bonds it needs, it's in files under unit 2. Okay.
Oh, sorry, I was not.
I also took a picture. I wrote it out because I.
Okay, so I'm new to
Gotta
it.
write it
I
out,
don't
but
know
I did take a picture of it.
But,
all.
Pero, a little careful. I mean, pero, persona. Huh? Exactly, just like 2 carbons, 4 hydrogens. Now you need to throw in 2 oxygens. That's, and there's only 5 there you need to know. Because the other ones are underneath in the periodic table.
So why is there arrows and
Why is there what?
arrows?
Okay, look at nitrogen up there, periodic table. What's underneath nitrogen?
Oh, okay,
Phosphorus. That's what the arrow points to.
okay.
And notice the dots are the same. And that's why the chemistry is the same for nitrogen and phosphorus. And that's why when they say groups have same chemistry, because of the valence.
Can you tell me one more time what the shell that you-
The-
This one that I.
Just one more time, I just need one, like the shells.
Yeah, it's at this stage though before you go to this. I mean, this is easier to see because you can see the dots.
Right.
This one, you have to know that's a pair of dots. That's a pair of dots. So after you get used to doing these, you can go directly to the line version. But until then, use this as an intermediate.
Okay, and that's the full shell.
Yep.
This one's the full shell, and then the hydrogen itself bonded with the oxygen.
Doing this is going to be like balancing chemical equations. It's like you do them and all of a sudden it's a aha moment. Oh, this is the way it works. Kind of deal.
And then I also had another question, in the book. Where would
So
this
yeah, that's
be,
what you're
like,
trying
what,
to do
is it in chapter
connect
2?
everything together.
No, chapter 2 is our unit 1. Yeah, so I need to look at the table of contents. But
Just like these steps.
the book does it slightly different than me, though. You can use the problems and then see their answer compared to your answer, but the process is a little different.
So,
So not to confuse you,
so I was just wondering for this next test, what chapter should I be focusing or should I just be focusing on your note for this next test?
my notes.
No.
Yeah, and the reason is the book's history is kind of scattered out about 5 chapters. They do it a little bit each chapter instead of putting it all together. So mine's real concise.
So watch your last lecture. I was here for the history, but watch the.
You were
last-
here for all of them.
Yeah.
So just a matter of just reviewing the videos. And any worksheets I reference. And if you want more practice on this also, if you go to well, you can start on dry lab for next week if you want some more practice. Because that's what we're doing in the dry lab next week, Lewis structures. I know, I keep forgetting to post the test for you. Don't worry though, it's not like it's gonna be, I'm not gonna accept it or anything like that. So, and you sent me an email about this, right?
I was just trying to make it like. Test
Yeah, so what I'm gonna do is I'm gonna post the test, and you're just gonna download it, print it, do it, and then, either give it to me or email it to me. But please remind me though, because I have 100 students and things are well. So if you send me an email, it'll float to the top. Do it tomorrow. Because I have off tomorrow.
Office hours by any chance?
I do, but they're by Zoom. So, yeah, just, say, could you help me with these problems with Zoom? And then, what's nice about Zoom is you can, if you email me the problem also, I can then post that on Zoom and then we can do it together. That works out really well. Did this make sense?
Yesterday and today. Went over my head a little bit, so I'm a little stressed about it.
Okay.
So I just need to make sure I get it.
And I have, lots of practice, on, Canvas files, Unit 2. A bunch of practice on this. You'll see like 4 or 5 worksheets on Lewis dot structures and, the history PowerPoints there, and just lots of practice. And then next week's dry lab is on this. So,
Yeah, so the take home question, they gave us the option to do last night. That was supposed to be turned in on Canvas, right? Okay.
No, you can email it to me.
Oh, okay.
So just, if you're,
I turned it in on Canvas, just send you an email.
Yeah.
Okay, thank you.
which schools